It's like the snail's pace. And we're good. All right, here we go. Welcome everybody to VJug's meetup. I'm so happy to be here with you. I am just getting some feedback. Sorry, I had the YouTube screen on. That was bad. Okay, so that was a false start. Let's start again. So again, welcome to VJug. My name is Lori. I am one of the meetup leaders here. And to my whatever side you see is Denis Magda, and he is going to do the presentation today. So let's just start with a little bit of housekeeping. Share my screen, as they say in every single meeting you've been in for the last 7 months. So here we are the virtual jug. This is my daughter. She is amazing. If you want to follow me, my name is Lori LaRusso. I work for JFrog. Very happy to be a part of VJug. We like to thank Sneak. They are responsible for setting us up with the Zoom and making sure that we are good to go. And if you are not in the VJug Slack, you need to be, because that's where all the magic is going to happen. Use the channel live session to ask questions. Denis is going to pause a couple times during his talk, so you'll be good to ask questions. If you've got feedback, use the virtual jug Twitter handle or hit OLAP, because don't hit me up. So today's session is in-memory computing essentials for Java developers and architects. And with that, I'm going to hand it over to Denis.
Hello everybody. What I like about this JAG group is that we can connect regardless of our whereabouts. So I'm located in California these days. I do believe that many of you might be connecting from faraway places. Let me quickly share my screen and then we will be good to go. All right. My slides. Looks like I need to refresh the slides. Wonderful. All right. I think that everything should be set. You should see my slides. And as an introduction, today we are going to talk about in-memory computing essentials. And let me first define what I assume under the essentials. I do believe that many of you already use various in-memory computing technologies. You might be using caches like Redis or Memcached. You might be powering your applications with in-memory databases such as RowDB or MemSQL, or you might be using different data grids and memory computing platforms that exist in our markets. But at the same time, all those caches, databases, and platforms, they vary in capabilities and features. But at the same time, there is something unique, something universal that unites all of them. Some fundamental or essential characteristics that belong to every in-memory computing technology, regardless of its primary use case. And today we are going to talk about those essential capabilities, so that once you know these essentials, you will be able to understand much better how those systems are designed, what are the generic optimizations, and then depending on your specific use case, by knowing these essentials, you can go ahead and select a specific technology, let it be a distributed cache or distributed in-memory database or anything else. A little bit about myself. For the last 5 years, I've been working with distributed in-memory systems. I'm gaining practical experience by contributing to Apache Ignite. That's one of the projects, top projects of the Apache Software Foundation. And they're going to use this project as a reference platform during this talk today. Also, I have a luxury of running developer relations group at GridGain, which helps me to work with many software architects and developers who build in-memory systems. Before that, before in-memory distributed software, I used to work for Oracle and Sun Microsystems for a pretty long time. My zone of interest and responsibility was GVM and GDK for mobile devices and embedded devices. And also my professional career started at the technology evangelism group of Sun Microsystems. Those days, I was spending all my time talking about Java, building communities, NetBeans, Solaris, and all that stuff. So what's our agenda for today? And let me also do this. Lori already mentioned that we have a Slack channel. I already have that Slack channel live session open, so don't wait till the end of this presentation. I will be taking pauses after every section ends, and I will be checking if you have any questions. So don't delay. If anything is unclear or you need more clarity, just post your question and I will get it answered throughout the presentation. So, but what's the agenda? We will start with in-memory computing. We will ask ourselves a question: why do we need in-memory computing? The question is obvious, but I will try to put ourselves on the same context, on the same page. Then I will spend 3 or 5 minutes of your time briefly introducing you to Apache Ignite, just because that's the reference platform I'm going to use throughout the presentation. I'm going to show you some samples, demos, optimization techniques. But nevertheless, all those essentials that we are going to cover, such as data partitioning, affinity collocation, and collocating computations, I will be demonstrating and explaining how they work for Ignite, but at the same time, all of those, if not most, like most of those capabilities are fundamental and they exist and supported by other distributed memory systems, right? Okay, first thing first, why memory computing? Why do we need, why do we even have this conversation today? So generally, the goal and the beauty of in-memory distributed memory systems is that they give us speed and scale. That's what they were created for. How the scale is achieved, the idea here is simple. All those distributed memory systems, they build to become scalable, horizontally scalable, which means that if you have an application that is now connected to a 3-node cluster, and at a given point in time, that cluster size is enough for you. It fits all the data you need, and it can sustain your current application load. Then, whenever you need to put more data into this cluster, or you need to add more CPUs to your cluster, what do we do? We basically scale out our distributed system. We are adding more nodes. If you need more, you keep doing this until you are getting to a desired cluster configuration. So that's the scalability aspect of distributed memory systems. They can scale horizontally, kind of giving you a boundless memory space. And when it comes to the speed, I usually like to use some precise numbers. And here is, that's one of the tables that you can find on the internet. That's not my invention. So what we have in this table, in the very first column, we have various system events, such as CPU cycles, level 1 cache access, etc., etc. And the second column, we have the actual latency, or how much time does it take for a CPU to complete any operation to the left. And the last column is the most interesting for us. Why so is that? Because the actual latency is measured in nanoseconds, microseconds, and milliseconds. We do understand that those units are extremely low, but at the same time, we, humans, live in a universe where everything is measured in seconds, minutes, and days. We can comprehend. You can physically sometimes sense the difference between seconds and days or minutes. That's why what the author of this table did, he assumed that, all right, if to put that one CPU cycle, which is around 4 nanoseconds, is equal to 1 second, and then we translate the rest of the latencies, we are getting this scaled latency that is adapted for our human universe. And once we do this, let's right now pay our attention to the following rows. The main memory, the difference between the main memory access and disk I/O is like the difference between minutes and days in our universe. That's why in-memory computing software is gaining so much popularity. And that's why we are using all those distributed in-memory caches or databases for our applications, because of the speed, and the speeds come from this basic and fundamental memory characteristics, and also because those systems are scalable horizontally. Okay, if to kind of do a speed dating with Apache Ignite and introduce you to this technology really briefly. Let me quickly check the chat window. It looks like, yep, it looks like some of the guys, yeah, we're not able to see the video, but hopefully that's already fixed. Anyway, there is a little lag between Zoom. We are using Zoom for streaming, and also everything is being pushed down to YouTube channel. Anyway, Apache Ignite. Apache Ignite is defined as a memory computing platform, and generally as a platform, it consists of many components. But I would define two primary components that comprise Apache Ignite. The first one is Ignite goes with a distributed multi-tier storage. And that multi-tier storage is broken down into a distributed memory tier and disk tier. So by definition, Ignite can keep data in memory, otherwise it would not be called a memory computing platform. And when it comes to your persistence option, Ignite can persist changes in your external database or in its own distributed native persistence. And on top of that distributed storage, Ignite provides a variety of APIs for various data access patterns. You can work with Ignite and query it with SQL. You can transact on Ignite. You can run key value APIs. You can run compute different custom Java tasks. How Ignite is being those are features. But if you ask me how Ignite is used in practice, what are the most dominant primary use cases of that product? I would define two. The first one, Ignite, is a cache. So let's say you have your database that needs to be offloaded, or you might have some application that is already choking and you want to offload that application or speed it up as well. And in this case, you just go ahead and deploy Ignite in between your database and application. And this configuration looks familiar to the way you would deploy Redis or let's say Memcached. And then the question might be then, why would I use Ignite and not Redis in this configuration? And I would say that people who use Ignite instead of Redis for this configuration, they are looking for SQL capabilities or distributed transactions or compute tasks. And if they need any of this feature like SQL, compute, or transactions, they would use Ignite. Otherwise, yes, they would go ahead with Redis. And the other use case of Ignite is Ignite as a database. In this configuration, nothing changes from the API standpoints. You're getting access to the same APIs. But the difference is in the way how Ignite persists your data. In this case, Ignite enables and uses its own distributed disk tier, and Ignite turns in a high-performance distributed database. In this configuration, you don't need to keep all the records in memory. Ignite keeps all the records on disk. When you, for instance, run SQL queries, Ignite will query both on disk records and in memory records. And if you restart your cluster for any reason, you don't need to wait while all the data is preloaded in memory. Ignite can always serve all the data from disk. And finally, this marketing slide, but I always find it handy. Ignite is one of the top 5 projects of the Apache Software Foundation, and we have more than 350 top-level projects there. And apart from Green customers, we have a lot of the companies that use the open source, that use Ignite open source version, and you can see those to the right. All right, guys, that was the introduction. Hope it makes sense to you. Let me check if we have any questions. All right, I think that we still have some, it looks like some of the guys have some issues with the connectivity over the YouTube, but anyway, let me carry on with this. What we learned so far, before we proceed with the essentials. We learned that why we need memory computing software in general, because those systems are designed to be scalable and extremely fast. And we are introduced to Apache Ignite. That will be our reference platform throughout this conversation. So what's the next thing? Right now, let's carry on and review the very first fundamental thing that characterizes every distributed memory system, regardless of whether that's a cache or database. We are going to talk about data partitioning. By knowing that data partitioning, you will understand how how an in-memory system distributes our records across the cluster. And once you know that, you will be able to come up with any optimizations or settings that would help you to influence the distribution. So let's take a look. But let's start from scratch. And also, I think that many of you might know the partitioning under a different name, sharding. For me, it's all the same. I don't see a big difference between partitioning and sharding. So first thing first, relational databases. Let's take those as an example. All our standard and databases like Postgres and MemSQL, they usually keep all the records on a single machine. And the perfect thing here is that once a request arrives in the database, all the records are on the database and we can quickly execute our operation, not involving any network round trips any longer. And when we are dealing with distributed memory systems, we somehow need to take all those records and distribute them across the cluster of machines. And this distribution happens thanks to the partitioning. That's the goal of partitioning. So right now, let's figure out what we as application developers and architects have to do, and what's the role of their underlying platform when it comes to the data distribution. I'm going to use this sample world database schema throughout the presentation. That schema goes with 3 tables. We are going to have countries, we are going to have cities that are obviously located in one of the country, and also we will have their country language table, because in many countries people speak different languages. Okay, so partitioning, first thing first, let's start from the very beginning. When you're creating a table in Ignite or any other in-memory database, you can use create table command to the left, and that's all you need to do. You just execute this command, and then what happens next is being done by the partitioning algorithm. So your table will be created internally, and that table will be split into a fixed number of partitions. You would have partition 0, 1, 2, up to some maximum number. For instance, in Apache Ignite, the default number of partitions is 1024. Once this step is happened, we need to take and spread those partitions across the current cluster. And that's again will be done by the partitioning algorithm. For instance, we can assume that partition 0 and 1024 would be placed on the first node, the other partitions will be placed on the other node, and that operation will be continued until the partitioning algorithm will spread all the records, all the partitions evenly. All right, that was the very first command, the very first operation. We created the country table. We just executed that DDL statement, and what happened internally, the table was created, split into the partitions, and partitions were distributed across the current cluster. The next obvious operation we would do is, all right, we've got a table. Right now, let's put some records in. That's why we would go ahead and might execute operations such as insert into country. In this case, I'm inserting the record of the United States, and let's see and that's all I need to do. And then what happens internally, the partitioning algorithm will take my primary key, which is the value of the code field in this case, and it will use a special hashing function to map the value of this primary key to a partition number. Once the partition number is identified for this given record, the same partitioning algorithm will decide where this record needs to be placed, because the record right now, let's say, is mapped to one partition, and that partition is located on some of the nodes. That's why that record will be placed there. So if to assume that United States primary key was mapped to partition 5, then this record will be located on the 3rd node, because right now that node owns that 5th partition. Okay. And we just explored the very first essential thing about distributed systems. That was partitioning. And before we carry on further, let me stop for a second, because I want to show you a sample application. Let's do this. What I'm going to do, I'm going to start a 2-node cluster, Apache Ignite 2-node cluster on my local laptop. Then I'm going to load that world database in the cluster. And finally, I want to see how Ignite distributed my records, because all I would be doing, I would just start my cluster, load the data, and that's it. the rest of the magic happens internally. That's how distributed in-memory systems work. All right, what I'm doing, I downloaded, let me show you what I've done beforehand. I downloaded one of their versions of Apache Ignite, and right now I'm using this script that is shipped with Ignite that starts a cluster node using a configuration. In this configuration, I don't have anything special. I just defined some memory parameters and some network settings so that all the nodes can auto-discover each other on my laptop. All right, I'm starting the first node. And I'm lucky I've got the first node started, but we are talking about distributed systems. Let's repeat the same operation. I'm going to use the exact command to start the second node. Wonderful. Now I've got 2-node cluster running on my machine. And as I said, the next step, that cluster is empty right now. I don't have any tables created, neither any data loaded. So that's why I'm going to use SQLite tool. That's an open source tool for lightweight SQL connectivity. From that tool, I would connect to the cluster that is running on my local laptop using Ignite JDBC driver. That's all I need to do. So let me connect to my cluster. I'm connected. Let me show you. Yes, I don't have any tables. That's the command that is supported by SQLite. And the next step, I want to preload the database. Let me use this script. And while the data will be loading, I will show you what's inside of this script. All right. Let me open IntelliJ here. So that script is not that different from any scripts you would have for, let's say, relational databases. So here is I'm creating country table, defining some Ignite specific parameters. Then I'm creating city table, country language table, and then I'm inserting all the records. That's all I, as an application developer, need to do. I'm just creating country, I'm just creating city, I'm loading the data. And then what happened internally? Let's figure out how the data was distributed, because that was the role of the data partitioning algorithm. I'm using this GridGain Web Console tool. And here is, I'm already connected to my local cluster. These are my 2 nodes. And these are my tables. That's how many records I have. But right now, I want to see how many partitions I have and how the data is spread across those partitions. That's why let me select the city table and then click on the partitions tab. So what do we see here? We see that 518 partitions were moved to the first node, and the rest partitions are located on the other node. Also, when you want to see how the data is, how many records I have inside of every partition, we can use this table. For instance, partition 0 is located on the first node, and in that partition, we have 3 records. Partition 1 is on the second node, and we have 2 records. So you can see that all the data, all the partitions were distributed automatically. And the partitioning algorithms, there are several most popular ones that exist. Their goal is not to achieve the even distribution, 100% distribution, but generally they try all their best to ensure that the data gets distributed kind of evenly, as much as possible, but that's not the primary goal. And why were we looking into this data partitioning thing? Because once you know how the data gets partitioned and what the data partitioning algorithm does, then whenever is needed, you can influence the way your distributed memory system places your records across the cluster. And today, the next section is, let's talk about affinity collocation, because this concept, this is essential thing, helps you to group and store related data together on a single machine. And once you start applying this technique, you would influence the way how the data is stored in your distributed memory cluster. So let's see what happens by default when you are not using any affinity collocation or any data grouping. So we already created country table and city table. And let's assume that the record of Canada is located on the first node and the record of France is located on the other node. And what happened here, I see that some of the Canadian cities are stored together on the same machine. I'm talking about Toronto and Calgary, but also I see that Montreal and Ottawa are located on the different node, those Canadian cities. And the warning sign suggests that that's not an error, that's not a criminal situation, because that might be absolutely fine for you, such default distribution, unless you execute some complex operations that, for instance, need to join your records of country and city table, or need to traverse all the cities that belong to the same country. If to take this example, I am executing a SQL query with join. I'm joining the city and country tables. And the goal of this query is to return the most populated countries or the most populated cities in countries such as Canada and France. All right, this query is being executed from my application. Then this query arrives in the server nodes that store the records. And once the server nodes come to their phase when they need to join two tables, they will figure out, some of the records are missing locally. For instance, when the first node needs to join Canada record with the rest of the Canadian cities, it will find out that some of the cities are not available locally. And those two nodes will start communicating with each other and shuffling records over the network. For instance, the first record would load Ottawa and Montreal from the second node so that it can complete your join query properly. In this example, we are just shuffling 3 nodes, and the impact of this data shuffling phase will be unnoticeable. But imagine if you're running a kind of a similar query or something like that, and joining the tables when you need to join thousands or like hundreds of records, and when you need to shuffle those thousands or hundreds of records, your performance and all the benefits of your distributed in-memory cluster, can evaporate like instantaneously. Why so that? Again, if we return to the very first table that we used at the beginning, when we were comparing latency time between memory access and disk access. Right now, let's see what's the difference between disk access and network. It's like the difference between days and years. And that's why you can be solved that, yes, just go ahead and deploy that distributed memory system because you can scale the data and execute everything from memory. But the problem is that all those distributed memory systems are interconnected through a conventional network. And a network is much slower than disk. That's why your goal as a software architect and developer to do all the possible optimizations so that you can reduce a possible negative impact the network might have on the performance of your applications. So with this use case, when we're joining tables of like city and country tables, we can easily fix this and address this. What we want to achieve in our cluster, I want all the cities that belong to the same country to be stored or grouped together on the same cluster machine. So generally what I have on this slide, I see that all the Canadian cities are located on one node and all the cities of France are stored on the other node. And how do we achieve such distribution? It's all easy. We as application developers, we need to do 2 things. First of all, you have to understand our business model. What are the relations between our business entities? And when it comes to countries and cities, the relation is obvious. A city can be located in one of the countries. And then you need to define an affinity key. So what happened here? With country table, it's all obvious. We have primary key and we selected country code as the primary key. But when we are creating the primary key of the city table, we are saying that the primary key will be compound. It will be comprised of the ID and country code. And then we are adding a special extra parameter, affinity key, which is equal to the country code. And this, once you do this, the partitioning algorithm, when it will be inserting your city records into the cluster, it will be using the value of the country code to calculate the partition number. And then once the partition number is calculated, your partitioning algorithm will know where to place this record. And it's not surprising that as long as all the cities that are located in the same country have the same value for the country code, then the partitioning algorithm will place all those records on the same cluster machine. That's it. And to do that, to achieve that, all you need to do is just to define this affinity key. Once this happens, and once you collocate all your records, group them together, and if you run the same query, you will see that the query will arrive to the nodes will join the tables, and there will be no any data shuffling phase. So you achieved the primary goal. You eliminated the negative impact of the network that would have on the performance of your calculations. All right, switching back to the demo. To remind those who might have joined us later, we have already started a 2-node cluster of Ignite. It's running on my local laptop. I preloaded the whole database. And the next step for me, let me go to GridGain Web Console back again. I'm going to use one of the SQL notebooks I prepared beforehand to demonstrate how the affinity collocation thing can be set up and how it can influence our performance. So let's run this query first, just to do a sanity check. This query returns the most populated countries, China, India, and United States. And the next query is the query of our interest. It's similar to the query I was showing on the slides, with the only difference is that here I want to get the most populated cities across all these countries. All right, I'm executing this query, and the answer suggests that the most populated cities are São Paulo, Shanghai, and Rio de Janeiro. But I know that's not the right answer. The thing with Ignite is that you remember the data shuffling phase that we have. So let's first thing first, the data is not collocated right now. All the records of the cities are spread randomly, which means that some cities of the United States can be stored on one node and the other can be stored on the second node. And practically, Ignite should have went ahead and used the data shuffling, right, during the join phase. But Ignite requires us to ask it explicitly if you want to enable the data shuffling between the server nodes. That's why I need to enable this flag. I'm allowing Ignite to execute so-called non-collocated joins. Non-collocated joins mean that we know that some tables are not collocated, and we want Ignite to shuffle records during the join phase. So once I execute this query right now, first thing that you would mention that the duration was like 2 seconds versus 42 milliseconds. If I execute this query once again, yeah, it will be around 2 seconds, the execution time. But at least I'm getting, right now I see the right answer. These are the most populated cities across these countries, Seoul, São Paulo, and Shanghai. We've got this, with the help of data shuffling, we've got a correct answer, but the execution time is bad, right? We need to fix something. And how do we fix it? Right, we need to go ahead and collocate our records. We know that there is the relation between city and country tables. To do that, let me open this script. I'm creating country tables, I'm creating city table. I already see that country code is used as part of the primary key of my city table. And the only thing I need to do is to set the affinity key. I'm saying that affinity key is equal to country code. Once I do this, the partitioning algorithm will be using the value of this column, and it will place all the cities with the same country code on the same machine. That's what I need to do. As long as I change the way how the partitioning algorithm decides how to map a record to a partition, I have to reload this database. I have to reload the city table. Let me do this. Once the reloading completes, the records will be placed and grouped together. Okay, it's over. Just in case, let me refresh this screen of the tool. I no longer need this allow non-collocated flag I'm unchecking it because right now I know that all the records are collocated. And when I execute this query, I can see that, all right, I'm getting this right answer. Seoul, St. Paul, and Shanghai are the most populated cities, and it took me like 11 milliseconds versus 2 seconds to complete it. And all I've done, I just set up that affinity collocation between the records, and that helped me to eliminate the negative impact of the network on the performance of my queries. And that's why, and affinity collocation is one of the most probably fundamental and powerful things that is related to distributed systems that have to be in your toolbox. Usually, I would say that many distributed in-memory systems support it, but especially you can find this feature available in distributed in-memory databases. It can be MemSQL, or it also can be Oracle timestamp scale out and many others, because those systems also support SQL with joins, and when you do join, you would better to collocate to group together your data. Okay, before I move on, let me quickly check the chat window as I promised, because we have plenty of time. The first question: shall we use OLAP and OLTP in Apache Ignite? So with Apache Ignite is used for analytical use cases, but also I would warn you that Ignite is not a pure analytical database. Ignite's storage engine is a B3 storage engine. So basically a B3 storage engine that is something similar to the engine you would find in the relational databases. But as long as, so if you don't need any columnar store, anything like that, then you're good to go with Ignite. And in my practice, anyway, people use, so if you can easily move your workloads to that B3 distributed in-memory engine, then you're good to go. And I know many companies that do this. But also, just as a precaution, do not compare Ignite, let's say, to Snowflake or any other classical analytical databases. So if I understand it correctly, Ignite is an open source answer to Gigaspaces. It's also based on Giny, or is it a complete separate? Ignite, I know that Ignite is used for some of the use cases that you would select Gigaspaces for, such as in-memory data grid. But how Ignite is different, let's say, Ignite can be used as a distributed database. Ignite has its own native persistence, which turns Ignite into that distributed database that not can only keep data in memory, but also it keeps all the records on disk. And once you keep all the records on disk, you do not need to preload everything in memory. Ignite can query both in memory and on disk records in real time. And once you enable that feature of Ignite, you also don't need to wait while, let's say, Ignite reloads all the records in memory if you have any restarts. If you restarted your cluster and you have petabytes of data in the cluster, you don't need to wait for like many hours while the memory gets preloaded. You can activate your applications, and applications will read all the data from disk. And also, I would say that Ignite supports standard SQL. It's not a custom language, so those who use SQL, it will be much more easy to switch to Ignite. At least those are two major things. Probably something else like more advanced transactional support. Okay, and thanks for your questions, and keep going, keep asking them. And while you do this, I'm switching to the last part, to the final essential capability. So to remind you, the first one was data partitioning. And why did we look at that feature? We just want to know how distributed in-memory systems distribute our records so that when it's needed, we can influence the way the records are spread across a cluster. The second essential thing was affinity collocation, because that feature helps you to eliminate a negative impact the network might have on the performance. And also with that feature, we have already seen how we can influence the data partitioning distribution. So keep that powerful thing in mind. And the last thing is collocated computations. With collocated computations, you can even went further and start running your complex business tasks right on the server nodes. So here is, if to give you an example, with the previous, when we were exploring the affinity collocation section, I was running just one SQL operation. But right now, let's assume that I have some business operation, multi-step business operation. First step might be execute this query, get some data, then do some calculation, then proceed with the second step, again, read some data, write something back, and do this back and forth until, let's say, you complete your whole business operation. And when you run this business operation, you might have a lot of network round trips and data movements between your application and your cluster. And here is again, the data is being moved over the conventional network, and the network is slower, right? It's much slower than disk. That's why what else can be used to eliminate the network usage or minimize the network usage? We can create our custom logic and execute that custom logic on the cluster nodes. You are already familiar with this concept if you have ever worked with Hadoop or Spark. For instance, in Hadoop, we have MapReduce Framework. And the idea of the custom logic in Ignite or in systems like Gigaspaces or Hazelcast that also support this feature is that you can create a custom Java task. Then this Java custom task will be mapped to your cluster nodes. That task will be executed over the local data on those nodes. And then those nodes will respond to your application with some possible result set, and your application can reduce that result set to something final and return to your application code. And what's happened here is that instead of executing the whole business application on the client side and putting data back and forth, instead we just took our logic and executed on the cluster machine. Here is, let me probably, instead of showing any examples, let me tell you a real story I was involved in. Like many years ago, I was helping, those days I was working as an engineer and a solution architect, and I was involved in a I was helping one big bank to deploy Ignite, to switch to Ignite and to use it in production. And that bank had one common operation, business operation, that had to be executed once a month. So the bank stored millions and millions of savings accounts. And once a month, late night, when the load on the system was minimal, the bank would run a special task, like a special application. That application would connect to a relational database and would read, sequentially all their savings account from the database, bring those accounts to the application, would do some financial calculations, then at the end apply the interest rate, and would write back all the updated savings accounts. And it took the bank 2 hours and 20 minutes to complete these operations. Not because the relational database is slow, the relational database is fast, but because they were moving all those millions of accounts back and forth from the database to their application. And they were not able to use stored procedures because they were required to use some advanced financial libraries to do that calculation. And when they moved to Ignite, and when they preloaded, let's say, those records into a distributed in-memory Ignite cluster, the very obvious thing they did, they, instead of using, let's say, they started using Ignite SQL queries. They collocated all the records, everything was stored together, they used Affinity collocation. And they've got a little speed up for that operation. With Ignite, that operation was completing in 1 hour and 30 minutes versus 2 hours and 20 minutes. It was faster, but it was not tremendously faster. And then we decided, all right, guys, why do we do this? Because the problem was that we still were moving data from Ignite to the application. And then we turned that business calculation into a compute task. And we started executing that compute task on the cluster end. And guess what? Once we did that, the execution time of this operation was dropped down to 11 minutes. 11 minutes versus, like 2 hours with the relational database and 1 hour, 30 minutes with Ignite and SQL. And all we've done there is that we just used this custom logic and the logic executed there. We eliminated the network. And keep this in mind. And that's probably one of the most crucial things I'd like you to take away from this meeting, from this presentation, is that distributed memory systems are extremely fast. But also don't fall in a trap that you don't need to do any optimizations, because those systems are interconnected over the network, and a network is slow. And your goal as over an architect and developer is to do everything is possible so that you can minimize the network utilization while your application interacts with your cluster. And that's why you need to keep in mind the affinity collocation, and that's why you need to keep in mind these collocated computations. So at least those are two primary and the most essential things that you need to keep in mind, okay? Before we do the summary, we still have 15 minutes left. Probably let me quickly show you how they're. No, I'm not going to show you any samples. Yeah, let's keep more time for Q&A. If you're interested, you can use Ignite or you can use any other system to see how those distributed computations work, or you can always reach me out and I will show you some samples. So as a summary, again, I will repeat myself. It's not enough just to put data in RAM and achieve nirvana. It doesn't work this way. The nodes are interconnected on the network, and sometimes you have to do some good architectural decisions before you move your distributed memory system in production. And the very first things that you have to be aware of when you're switching or start building anything for distributed memory system is data partitioning algorithm, because you need to know how data gets partitioned, because if you know that, you know how to influence the data partitioning whenever it's needed. Second, affinity collocation. You want to group your data, especially if you're executing complex queries such as SQL with joins or collocated computations. And final thing, the third one, collocated computations. That's a feature that allows you to execute your custom Java tasks on your cluster nodes. And if you do this, you're just minimizing or eliminating the network usage. And that's great. And also, I'm a believer in education. So what I've shared with you today is something fundamental and characterizes distributed memory systems. But also for those curious minds who would like to dig deeper, I would suggest several books. If you'd like to understand more details on how, let's say, not only in memory distributed systems, but in general distributed systems are designed and operate, start and look at this Designing Data Intensive Applications book. That's an excellent, even if I also I've been with these distributed memory, I'm working with these distributed memory systems for the last 5 years, but still that book was extremely useful for me. Once you read this book, if you want to dig even deeper, switch and check the database internals one, because that one explains you, gives more details on the various storage engines, because some databases are B3 storage engines such as Apache Ignite. Also, we have classical key value stores, or we have NoSQL databases that are log-based storage engines, etc., etc. Check this out. It doesn't matter whether you are building a distributed database or contributing to it. Even those books are great if you're just building your applications and services. And today we are raffling these books. So here is, you can see on this slide a link to the raffle. So while I'm responding to the questions, take part in this raffle, and you will get a book mailed to your door. You will get a printed version. All right. Having said that, let me quickly check the chat. What we've got here. The question says, how does data with same affinity key scale? Does special consideration for bucketing data need to be thought out before designing? Yeah, that's an excellent question. You're right saying that, because it might happen that there are too many keys that have the same affinity key, and you can end up in a situation when, let's say, you physically cannot longer place that partition within your given, let's say, physical machine. In this situation, there are different bucketing techniques. I don't have time to explore them today, but general, once we were involved in another project when Ignite was used for, let's say, for credit card payments processing. And in that case, the data model was as follows. We had different merchants, and for every merchant, we stored a history of transactions. And the very first optimization was, all right, we grouped together all the merchants with the transactions, but then we found out that we have big merchants such as Amazon and Walmart. And it's just impossible to keep all their transactions that belong to Amazon on a single machine. And then, yes, we started, creating some custom bucketing schema, like when the records were still grouped together, but those groups were spread across different nodes. Right now, with Ignite, I think that probably in a year or two, Ignite might have this feature out of the box. Google Spanner supports such feature out of the box. But anyway, if you get to this situation, there are some techniques that will help you to influence the way how data gets partitioned. The other question, will Apache Ignite work on container environment? Yep, Ignite doesn't matter. You can use it on clouds, containers, Kubernetes, Docker, or you can run it on bare metal. It's up to you. Just check with Ignite technical documentation, and you will get more details. One more question: how different is Ignite versus Redis with regard caching? So here is. Let me show you the slide I used at the very beginning. This one. So Ignite is a cache. You would use Ignite as a cache if you need SQL. So Ignite supports standard SQL language like joins, groups by sorting. Redis, at least at the moment, does not support standard SQL yet. Also, those people who use Ignite, they might want to use transactions through distributed transactions that can change your records that are stored on different nodes, multiple records in different tables, etc. And also custom logic. Today we were talking about the collocated computations. Ignite allows you to execute custom Java tasks. You can use any APIs right on the cluster node. In those situations, you would use, let's say, people use Ignite over Redis. If you need SQL, collocated compute, or transactions. And also another thing that is sometimes important for guys is that when Ignite is deployed as a cache on top of your, let's say, relational database, Ignite can take responsibility for the synchronization between the cluster and your database. So whenever anything is written to Apache Ignite cluster, Ignite can write through all those changes to your, let's say, Postgres, Oracle, or whatever database. With Redis, it's on you. With Redis, you have to update both Redis and your database. So that's the difference. Okay, the link to the Raffle. Let's do this. Let me show the slide once again. I pasted that link in the chat before, but let me do this. Okay, that's the link. Guys, if you have any other questions, please go ahead. If not, I'll give you 1 more minute to take part in this raffle, to fill in the survey, and after that I will switch and I'll do the raffle because we have like 8 minutes left. All right. Okay, let me go to the Raffle page. Bear with me. Today I have to do everything on my own. Hectic days. View responses. All right. And how do I select the winner? All right. And the first book, Designing Data Intensive Application, goes to Casimir Rex. I am writing down the name in the Slack channel, Designing Data Intensive. Congrats. So my colleague will reach you out over the email that you provided, and she will figure out how to mail the book to you. What's the best way to do that? Okay, the next book, Database Reliability Engineering. Let's see who gets that book. That book goes to Neishatha Sivalia. Sorry if I mispronounce your name. I'm writing down the name in the Slack chat window again. Reliability Engineering. Again, my colleague will reach you out, and again, so apologize for the mispronunciation. And the final book goes to Database Internals, the most advanced one. goes to Maria Arias de Reina. Congrats. You'll get that book mailed. Database internals. Wonderful. All right, folks. You've got 5 minutes left. If you have any other questions, please go ahead. Otherwise, you can always reach me out on the community channels. I'm always hanging out with the Ignite community, or you can direct message me on Twitter. It was a pleasure. Unfortunately, I wasn't unable to see you, but hopefully this presentation was useful.
I want to thank you, Denis, on behalf of VJUG for presenting. I do want to, again, apologize for the link mix-up. So I have a feeling we have quite a few people that will be watching this in replay to catch the first couple minutes. If there are no other questions, I'm going to go ahead and sign off and say thank you very much for being with us today. Stay tuned to the Meetup channel. We've got lots of other sessions coming your way. And again, thank you, Denis. And for all those that won books, congratulations. And everybody have a good and happy rest of your day. Thanks so much.
Thanks, everybody. Bye-bye.